Good. So I think we've got a few people joined now. We may have some more joiners come in later, but I'll quickly introduce you, David. So yeah, you're now in the Netherlands. Is that correct?
Yes.
Yes. Okay. And yeah, I've been looking at your website, and you've got a really diverse portfolio of research interests and commercialized a lot of different areas of your work. So you've got some bubbles, which you're talking about today, also needles. And I saw that you're doing some hydrogen and energy research as well. So I can't say we have anyone here doing bubbles or needles, but we do have someone doing hydrogen. So yeah, but I'm sure what you'll be talking about is applicable to all of our researchers, many of whom are looking for ways to commercialize their work. Some have already done so, like Nick. Magda's trying to commercialize something at the moment. I know Casper's been interested in that, so, and Mikhail as well. Yeah, so we're really interested to hear what you have to share with us today. And yeah, I'll hand over to you. Do you have slides that you want to share? If you...
Yes, so I'm planning to share my screen, and well, thanks to you all for allowing me to speak today. I just realized after you said that well, the slides I didn't choose to share today are the ones about the hydrogen, because well, it's the one that is the farthest away from any utilization. But well, let's see if we have time. I can probably tell a little bit about what we're trying to do there. Let me move this thing. Okay, so how do you see this, or can I make it go away?
Yep, no, you can see that.
But is there a way to hide it? I don't use Zoom that often, so it's
okay. On my screen, there's nothing blocking. There's
okay.
We can see the Cambridge CARES logo at the top of the screen.
Okay,
so
perfect.
It looks good to me. Yeah.
All right. So are you ready?
Yes, I think we're ready. And yeah, if anyone else joins, I'll just let them in quietly.
All right. Well, again, thanks for having me here. I will try to give you a bit of a flavor of my adventures trying to valorize scientific research. I recently reshuffled some slides, and the format might not be as typically I would like to, but I think the story is there. And I tried to keep it to the 20 minutes that was requested, so that we can have more time to exchange questions. So basically, I have a small group here in Twente. So most of the things I will be sharing today is the result of teamwork. So obviously, I'm not able to do all by myself. And this is a picture with almost everybody who's currently in the team. It's a late snowfall. I think it was like April. And we went to campus and took this picture. So as you can see here, we're making bubbles with a bubble gun. So actually it's like a soap gun that you can make bubbles. So I will be talking a bit about having fun while we make bubbles. As I said, I left out the hydrogen part because it's the one farthest away from commercialization, but I'll probably, I can answer some of the questions of the people interested, but I'll try to first cover a little bit about the trajectory that started with my PhD. And it's a company already operating for a few years and with a product on the market. And the second point is a bit about this sort of needle-free injection that Luis just mentioned. So my general vision here at the University of Twente is to exploit balls for chemistry and bioengineering applications. And I typically say applicable research to try to differentiate it from what most people know as applied research. So when you ask sometimes researchers like, okay, can this have some use in practice or in society? You say, yeah, well, I don't know, in 20 years or 50 years, or to make a very long connection to what they're trying to do. But my ambition is to really work as close as possible to the deployment into society. And that means that most of the times I'm very close to the, how to say, the entrepreneurial activities, like making sure that the patent is done properly and creating the company. And well, that has also an impact on the number of publications and maybe the impact of the journals that I would probably publish regularly, but it's a conscious choice. Now, so in a nutshell, I think I have another slide in a moment to tell you a little bit about my trajectory and why all this makes sense will be made clear in a moment. So basically, I'm trying to valorize and, as I said, bring the knowledge to society, and I see it as a constant activity. So the knowledge is this baton in the relay race. And well, basically, I have this sort of 3 or 2 main lines of research. At the middle, we have a bit of a common element. And well, today I will be talking a little bit more about this. For the hydrogen, probably we can talk later on. Now, I'm from Cuba. I did 1 year military service, and I started as a nuclear and power engineer my studies, and at the same time research activities as an undergrad, which allowed me to already go at a summer school before getting my degree in Germany. Then, well, I finished relatively earlier than expected, and I continue international collaborations in Italy. I got my master's, and at some point, after many conferences, I got an offer to do PhD in the Netherlands, which I accepted. And well, actually here, coincidentally, during my PhD, I had a chance to visit Singapore, a very interesting country. And well, finally, I got my PhD thesis, and here you already can get a hint of how I deal with complex issues. So that's the cover of my thesis, and I use humor. And in many of my presentations, I use art or allegories to, let's say, artistic representation. So you probably see one.
Well, yeah, that's the issue. Thank you very much.
Okay, thank you, Jakob. So at some point, I decided to start my company with a co-founder. I think I have 1 or 2 slides about this part later on. I became also a faculty member, and well, I've been in the process of starting a new company. You will see in a moment as well. I got tenure in 2017. I also became affiliated at the MIT. And in the last couple of years, things accelerated basically because of this big European grant. And unofficially, I was already promoted to professor, so adjunct, so I can dress with the funny gowns and toga. I typically say it's the Harry Potter dressing. Now, there's a point where I understood that most of the people listening today are, let's say, early stage researchers or in their PhD. So when I was finishing my PhD towards 2012, came the kind of a bifurcation. So like, do I go to industry or do I stay in academy? So I had the chance, like almost at the same time, to apply for this position. And I made very clear with the faculty, and actually they encouraged me to try to keep this dual character, because well, nowadays not everybody can really do it, but it's very important for scientific knowledge to be valorized in the most efficient way. So I kind of became the one-man orchestra, because you have to write papers, you have to write proposals, you have to teach, you have to also keep a personal life, and well, there's a lot of sacrifice, but I think in the end it makes total sense to me. I have enjoyed it, and I would recommend it to anybody who has a good idea. And even if you are not the founder of a company, you could also join a spin-off for 1 to 2 years. It can give you a lot of experience. And typically, there's this sort of a misconception that in academy, once you go to industry, you can go back. I found very successful professors that have had stint in industry or in spin-off companies. So the CV gets enriched because you bring a lot of knowledge and network that if you would have stayed in the academic sector, you wouldn't have. So if you are willing to do that, I highly recommend it. Now, I see that most of the names popping up here seem to be foreigners in Singapore. So one of the type of messages that I bring not only to foreigners, but also people living in the country, is that there are some things you cannot control. For example, the food here in the Netherlands is not the best. The weather is unpredictable, and they have some strange traditions, and every year there's a lot of political discussion. But then if you really focus on the positive and things that have potential, like better and tastier food, or very nice places, or even the freedom and the whole possibility for growth as a person, but also professionally, which I know every country has, then instead of focusing on the negative, if you focus on the positive, you will get better results. Now, shortly introducing the University of Twente. So we are typically trying to portray ourselves as the most entrepreneurial university in Europe. And some of the examples of companies that were either founded by graduates from our university or spin-off from the university are probably Booking.com, that you probably have seen. And well, this one is one of my companies. It's relatively small, but I like to put it in the lineup of the big guys because, well, it doesn't matter if it's small or big, it's how you bring a solution to a problem that society has. Now, again, our group, the name gives us a lot of freedom because mesoscale means that you can do from nano to bench scale and even larger scale. And there are other, actually, I think there's a new assistant professor. I have to update this slide, but since we are in Corona, I haven't really had much contact with the new prof. But we have, well, 2 clean room technicians, meaning that we do a lot of micro fabrication. And I think this number increased a little bit, the number of PhD students and postdocs. But this is just an approximation. Now, getting a bit more into content to teach you something today, when I talk about cavity or cavitation in the following slides, means bubble. And well, typically I like to bring this slide with a question to the audience. So I have a question for all of you. And if someone could tell me what this bubble can do. If you have an idea, unmute and speak, because if you say it with the microphone off, then we will never know.
Sorry, what is she doing?
So, well, what do you think this bubble is doing?
I think the kid's blowing in the bubble with like
yeah, I've just seen a bubble thing like that.
Yeah, maybe.
It can definitely entertain her. Yeah.
So it's relatively close. So basically, why I use this slide is to first indicate that the bubbles I will be talking today are not these ones. So basically, this is like gas outside. There's an interface, and then there's gas inside the bubble. Then what this bubble is actually doing is helping this little person here learning how to brush its teeth or his teeth. So I use this slide to bring into perspective that even though you are now, I don't know, in your PhD or early in your research career, you might think everything has already been invented. There's no chance for me to come up with a new idea. I will never make a groundbreaking discovery, and you might start thinking like, okay, ideally, most people should be brushing their teeth once a day. I hope you guys do it at least twice. And still this company in 2014 managed to bring this idea that only when the toothbrush is used properly generates a bubble. So it's an action that most people perform on a daily basis. And still, the whole idea of innovating doesn't mean that you're bringing something out of the blue. So typically, in my opinion, you are just connecting elements or technologies from different areas and bring it into some sort of new solution. And well, ideally, there should be a market for this sort of product or somebody actually waiting for this invention, but that's a second step. So with this slide, I want to motivate any of you that might be a bit discouraged by the whole innovation, entrepreneurial, big names. Sometimes it's a lot simpler than what it sounds. Now, if you get bored from my slides, I don't have any fancy questions. I have a few slides from now on, but if at some point you fall asleep or somebody calls you, on the phone and you have to leave, well, you have the recorded the recorded lecture, you can always see it. But well, these are my kind of personal message to you, and well, each of them in itself is kind of obvious, but I think if you combine them, like, well, persistence, but also flexibility and talking to many people, and as I said, there's always an opportunity that you can invent or innovate something. But then you definitely need to know where you want to go. And this can take time, but it's never too late to start your own company or joining a given venture. Now, there's a bit of bubbles, gaseous bubbles in liquids, and I think many of you have done a similar experiment. Let's see if the video plays properly. So when you put cola or carbonated beverage in a glass, you can see typically bubbles rising from the bottom or some imperfections on the inner side of the glass. So you might be wondering, what does this have to do with the whole topic today? So actually, during my PhD, I've connected this sort of activity of drinking, in this case beer, and the phenomena at hand actually had to do with improving the efficiency or the energy efficiency of sonochemical reactors. Now, sonochemical reactors means that with ultrasonic waves, so frequencies above the audible regime, if you agitate a container, you can create bubbles. But normally, researchers back in the day were focusing on the interesting phenomena around ultrasonic cavitation, such as light emission, shock wave, jetting, streaming, mixing, radical formation, for those who are chemistry in the audience. But not so many people were looking at how to control this. Basically, everybody was just cranking up the power of the reactors. And then at some point, the effect will saturate because, well, you could not get more chemical effects out of the input that you were bringing. So what I chose was to focus actually on where are the bubbles created, how can we control better the place and the moment where bubbles are created, and that actually ended up being a good approach because we managed to improve the efficiency by 1 order of magnitude, which is modest for industrial settings, but for research purposes, that's already a big step. So that's why I typically say, well, finish your drink, because if you don't finish, you wouldn't have seen at the bottom this sort of defect. And actually, in this case, is the manufacturer of the glass made this defect on purpose to guarantee the continuous stream of bubbles. So basically, that's what I did. And to illustrate, I have a video in the following slide. But in this slide, it's just summarizing what I just explained. So you agitate the liquid with an acoustic pressure. So you can get small bubbles, big bubbles, and there's a moment where they collapse. And the moment of collapse, imagine it's a combustion engine. The moment that the piston just compresses the gas inside, you have a big bang, and then this big bang allows you to create all this fancy phenomena. But, and this has to do with the next part of the talk, is that if the bubble is close to a surface, then this bubble during collapse can form a liquid jet, and this liquid jet can actually be used to clean or destroy surfaces. And this is why ultrasonic equipment is used for many purposes in biology and chemistry, for emulsification and, well, sample management. So this is an actual video of how these bubbles collapse. This is very fast phenomena. So the video I think I have in the next slide illustrates the access we have to fast cameras. And also, well, as I was saying, why this technology is not really mainstream in industrial settings. Well, the energy efficiency typically from the effect that you want, which is at the molecular level, is in the order of -6. So you put some electrical power at this scale, and then the actual effect that you have is almost lost when you measure the amount of radicals that you created. So what I did during my PhD and in the last couple of years is to try to control all the phenomena happening at the different scales, and then we have improved a lot, particularly the cleaning aspect of ultrasonic cavitation. And I have a couple of examples. So now this video that you can also find later on in YouTube kind of speaks for itself. I will let you focus on it, and then I can rest my voice for like 1 minute. So this is 10 million frames per second. And well, there's a bit of physics involved here. In late term, you can interpret it like the bubbles like to talk to each other. And this sort of talking allows us to steer the bubbles or use them for specific purposes. So there's a millimeter from here to here to give you a feeling of scale. And again, a millimeter from here to here. So that illustrates a good control of the spatial cleaning effect of this technique. If you wouldn't do this sort of artificial modification of the surface, so making these pits, then the cleaning will be random. And well, it might take longer to clean a given area. So with this concept, what we've done actually is to shorten not only the cleaning time, but also protecting the substrate you're trying to clean. And well, a question we typically get in microfluidics, how you get more, so you number up, you can have more of these pits. And you will see more examples in a moment. And here comes another of this sort of references to art. This is more like a prank. I say it's the acoustic bubble band, but we don't know what they are playing because it's ultrasound, so it's above the audible regime. And well, this is the funny part, but of course in the lab, at some point, my collaborator and I start thinking like, hey, maybe we could use this for something beyond, let's say, scientific publication. So the same experimental setup, we brought very close to those bubbles a contact lens that was painted with permanent ink. So this is a tweezer tip, and then, well, it's a non-optimal setting, but the moment that I managed to put the contact lens close enough to the bubbles, you can see how the color is removed. Later on, we did surface analysis on this contact lens, and we didn't see any damage, because typically the damage due to ultrasonic cavitation is done by fatigue. So after you really do it for longer periods, and maybe it's important to let know that that contact lens is not the one use type of contact lens that you throw away. These are more prescription contact lenses. So then my colleague and I decided to already back in the day to start blowing some bubbles. We founded our company with a very small subsidy from the government. I mean, this is literally nothing, 25,000 euro. And for a few years, we started doing consultancy, and we started thinking on a product that could help solving problems of specific markets. One of the markets that we chose back then was, as I mentioned, the contact lens manufacturing. And later on, this, for you to get an idea, this happened more or less in parallel to the explosion in 3D printing technology. So we found that some 3D printers have like a support material, and sometimes it's very hard to remove it once you have the printed object. So that's another of the markets that we try to approach with our technology. So why ultrasonic cleaning is important? Well, because you basically have 4 variables to control cleaning. One is mechanics. So if you want to come with a brush, temperature. So, you know, if you heat up something, you can clean faster. But you can also use detergent, or if you are patient enough, you let something dirty and then the contamination should fall off. So the advantage of ultrasound is that you don't really need to use the mechanic part, because the bubbles will do the cleaning for you. You actually don't really need to heat it too much. And the chemistry, still on the debate. Some people think that the radicals created by the bubbles can help in the cleaning, but I'm focusing more on the mechanical part and even the advantages to increase the efficiency, reduce the waste. And well, basically we came up with a product. So this is a short commercial. This is a small disclaimer. This is how the product that our company has been selling for many years. No angry customer has written back, and we have recurrent customers. So that's a good sign. And I typically say, don't buy it until you see it working. And for that, we have another short video. I don't know if you will be able to hear the music, but well, in YouTube later on, you can find the same video. This is way shorter than the previous one. Then, well, one particularity of what I've done in the last few years is that, so the company is running on itself, and I'm not involved on the daily operation. But in parallel, I've been publishing at least 6 to 8 papers with the same concept. So what we've done is propose the chemical engineering community to replace the beaker or specific containers that they might use on a regular chemical experiment, and use this bubble bag. The last of the papers that we published on this topic was to actually put some catalyst inside the bags and show improved oxidation processes. More details you can find on my website, or if you have more questions about this, please send me an email. Now, of course, it's a small company and we are slowly trying to grow, and we've gotten a few grants and small money here and there, but developing, how to say, equipment or heavy technology products is quite a long trajectory if you compare it to a mobile app or some sort of website service. So for those who want to go this avenue, my main message is be patient. There are many obstacles ahead, but if you manage to combine it with your own, let's say, science development or your academic trajectory, then it's worth the try. So I'm closing here the first story, and I have a small side step with a relatively simple joke, because one of the things that I think is interesting to show by doing this sort of commercialization activities with the bubble bags, we realized that it was difficult to convince customers that our technology was better than the standard way of doing things. So what started as some sort of industrial challenge became a scientific curiosity. So I wrote a paper and it got published and it's getting a lot of attention. And to summarize it, the question I pose typically in this sort of lectures is like, how can you compare, in this case, who's the best or the worst president? Does anybody has an idea or wants to propose for him, her, who should be the best, and explain why? Jacob, we know that your microphone works. I don't know if you are willing to.
Oh, did you hear me? Oh gosh, sorry. I've just been told that you did hear me. I'm not sure. I feel as if we should put this picture on one of your little bubble things and see whose face gets scrubbed off first, and that should determine who is the best president or worst president. Who's got the most sticking power?
Yeah, well, I mean, in view of time, I will move fast, but thanks for the answer. So basically, this I put it to illustrate that it's very hard to agree on something, because for some people will say, well, the tallest is the best, but some people are more into the left or to the right spectrum or political spectrum. So the same type of questions I had trying to convince customers, and we wrote a paper about it. Well, this is an old slide. It's already published for more than 3 years. But basically, we have a few examples in this paper showing how this technology is better in some sort of intensification factor or innovation factor. And I even recorded last year a pencast, so you can also follow it later. I will share later on the slides to make it easier for you guys. But then in a pencast during the pandemics, I tried to make it a bit easier to explain to students, since we are all teaching from home. But this actually it became quite popular. So I've seen, I think every week, a new citation of the paper, maybe a week. It's a bit exaggerated, but it's to my surprise picking up. Now, the next phase of the talk, and I promise to finish relatively fast, has another video showing some sort of popular science fiction video. I'm not sure if the audio will be there, but let's see how it works. So that is Dr. McCoy injecting Captain Kirk. I see most of the faces probably are too young to know. I was not even born, I think, when this video was made. So, but probably now you can follow Star Trek in Netflix. There's a newer, let's say, season. But the next topic I want to bring again follows the same line of thought. So needle-free injection was already in the mind of people for many years. Even in the 19th century, there was a French guy trying to inject without needles. And in the 50s, it was very famous that GI soldiers were vaccinated before being sent to Korea or Singapore. Malaria vaccinations in Africa were relatively successful due to this sort of a needle-free vaccination. And in the market right now, you could find probably 3 to 4 needle-free injectors. So why am I innovating in this field? No? Because you say, well, after so many years, everything probably is already discovered, nothing to innovate there. But actually, that is not totally true. So what we are developing right now is a bit of a more portable. For example, here you can see this is not portable at all. There's a big equipment. Sometimes, well, here you see here, you need some sort of compressed air system. Sometimes you have very portable devices, but they are limited in the energy that you can use. So they are like compressed springs. So basically what I'm focusing now is, instead of the traditional ways of injecting without needles, I'll tell you in a moment, I'm focusing on some sort of controversial application or less known medical uses, like tattooing, for example, when people have received mastectomy, men and women alike. So I didn't know, but men can also have breast cancer. But you can redraw the nipple, and this improves the quality of life of the patient, people who have lost hair. But with the same technology, my ambition is to have better treatments for other applications. We don't have time to go in all the details, but it's very interesting because we're similar to the slide I had with the beer glass. Most people were focusing here in the deep injection and larger volumes, but I'm focusing on very small volumes and low depth injection. And this is very interesting because it's running along the trend of personalized medicine. And we know that everybody's skin is different. So how can we inject in this layer where many vaccines and many treatments work better than intramuscular? So of course, for many years, there have been already tools used for this work. And well, depending on the treatment, you might want to go deeper into the skin, and you might even have microneedles and nanoneedles. And why it's important sometimes to target this layer is because the immune system tends to respond better when you inject vaccines, for example, in this layer. Now, the problem with needles, I should have warned that this slide is a bit sensitive for some people, but well, that's shaded very fast. So one of the problems with needles is that, well, people sometimes skip the treatment because they are afraid of them. This figure is kind of comparable to the rest of the world. But less known is that the health provider or the nurse or the doctor sometimes by accident can prick a finger. And this has very big problems because not only the risk of getting a given disease like HIV or other infectious diseases, but then this person has to take a leave and then for 1 to 2 weeks stay at home and check that nothing happened. So imagine now in this whole mass vaccination campaigns, if the people who are trained to inject by accident have to stay home, so the whole vaccination thing is delayed. So there's a bigger problem actually that most people are not seeing on a daily basis, is that we use, even before the pandemics, approximately 44 million needles every day, and this becomes waste. So whenever you have this sort of one-time use thing, you ideally should dispose it properly, but sometimes it ends up in nature. And then there's a last technical or a biomedical problem, is that when you use a needle, you leave a wound behind that needs to heal. And in medical tattooing, for example, the resolution sometimes is not so good, because basically you hack the skin to bring pigments into the skin. So you destroy part of the skin, which is not a good idea for a person that just had lost part of their own body. So the solution works relatively simple. I have, I think, a couple more slides. So we use a laser to heat a liquid, and then a bubble, and then there's the connection with the bubbles, push the liquid away because it grows at a very fast speed. I'll show you more videos in a moment, but you can also find the total lecture in this YouTube link. Now, how it works in practice is we use some different type of skin or skin surrogate. And what you will see here is the laser, you don't see the light itself, but we'll boil a bubble here in the liquid. And well, it pushes at velocities around the 50 to 80 meters per second. And in this case, it's agarose. But this video we used to illustrate all the different challenges. So you don't want the liquid to break up before entering the skin, like this. And you also want all the liquid to get inside the skin before this hole closes. So this is more or less the technological challenge which we are studying in our lab. So what is our trick? Again, using microfabrication, we are controlling the geometry. And actually you see now this other injection, the liquid keeps better this sort of elongated shape. And you will see penetration with no splashback. So it's a lot better, the contour in this case. And just check the timer here. So in less than 1 millisecond, this injection took place. Now, the question, does it destroy the skin? Is it painful? Well, we haven't gotten that far with the pain question, but we hypothesize that you should not feel much because first, the damage we have observed to the skin is minimal. We actually haven't found a hole on the skin, which means that there are two options. One, that the hole is so small that when we do the cross section, we can see it anymore, even though we see penetration into the different layers of the skin, or that the liquid manages to make its way in between the intracellular space, like this arrow indicates, which is even more interesting. Now, for the pain question, we need to do more experiments, but the hypothesis, and in conversation with experts, is that the size of these droplets and the time the injection takes place is so short that it's almost impossible to recruit the sensor cells that are involved in the signals that give pain to a person. And we compare it with the mosquito biting. So you don't feel when the mosquito is actually puncturing your skin, but you feel is the poison, or when the mosquito flies away, some effect. But the penetration itself should not be felt. Fast forward, we have protected the idea, we have published the patent, and we are in the process of signing the incorporation documents for a company that would be commercializing this technology or platform technology into different markets. And it should work some sort of like a handheld device. And this cartridge could have a medicine or could have ink. And well, in the future, will look something like this slick design, but this is more like a mock prototype. And I'm about to finish. For those of you who might be getting tired, I think my screen is flickering, maybe because of the data thing. And then, well, this is part of a bigger ambition I have of developing technologies that should go under our skin. And you can find 2 videos in YouTube. And then, as I said, of course, this is a work that has been done already since 2014. So I have had the help of a lot of students, PhD students, but also many professors and scientists all around the world, which I cannot put here because then we will probably need 10 more minutes. But obviously, if you compare the story of needle-free injection, it's a lot more interesting for the social media than cleaning. So that's why I said, well, cleaning is a dirty business. I probably got 1 or 2 requests for interviews when I came with big publications in very famous journals. But now here, sometimes I actually have to turn down the request for interviews and radio and videos because, well, people really would like to see injections without needles. So with this, I would like to thank you for your time. I think I took a bit more than I was planning to, but well, I apologize for that. And of course, the funding agencies that have funded all my research lines. And if you have more questions, just shoot now or check on my website, which I try to keep quite updated. That's all.
Thank you so much, David. That was really interesting. I have never thought about needles or bubbles like that before. And yeah, I learned a lot about the basics and also, yeah, the interesting innovations that you've applied to the topics. So yeah, open to questions. I did have one. Oh, Mikhail's got his hand up. So
yeah, you go first.
for it, Mikhail. Oh, me go first? Or?
Yeah.
Okay, right. Yeah, I was just thinking, and maybe this is similar to what others are wondering as well, but for your bubble cleaning company, how did you find clients, and did you sort of offer companies to test it out first before they took on a contract or bought equipment from you? So how did you kind of start gauging interest in that area?
Well, I think that is a crucial question, because you might have something in the lab, and the professor or the scientific community might believe what you have, but to convince people to open their wallets and pay for something, as you said, sometimes helps when you let them see how it works. So we had a multi approach. Like, we went to commercial fairs. We tried to publish not only on scientific journals, but more popular science blogs, made videos. So we have a YouTube channel where we show how it should be used. And on the academic sector, then of course continuing publishing papers. But then you can also approach, in this case, lab suppliers. So in some sort of distributors, you can convince them to put your product on the catalog. And we even, through that avenue, we managed to be finalists of the most innovative lab equipment from 2015, I think. So if you, it's like little actions in different, I'd say, channels, and slowly they start growing.
Yeah, that's really great. Yeah, and it's interesting that you used YouTube as well. So you kind of, instead of having to approach each company directly, you sort of had a platform where people could come and find that as well.
Yeah, because I mean, then you can use the same platform to let see, because our experiment is so small. It's not like I can make a video and show with my hand. So we had the access to the technology, all this fancy camera, and in very transparent conversations with the university, because that's also important. The relationship of the spin-off founders and the university is very important. If it's good, then you can do many interesting things. If not, you have to pay for everything. Then, well, you need more money, let's say.
Yeah. Okay. Oh, great. Thanks. Yeah, Mikhail, did you want to ask a question?
Sure. I actually have two. One is about your competitors. Yeah, there are a few. At least I know one in Israel. They have like those. Also using the ultrasonic stuff to impregnate, for example, particles or something like that inside, for example, metals or maybe some textile or whatever. So they also use
about the group of Professor Heranken in Bar-Ilan.
I actually forgot. Yeah, that's previous in my previous company. This professor was visited with a lecture for us, and he was shown that actually they can do the coatings with those gravitational effect, so they can put the nanoparticles inside some different surfaces, right? Yeah. So do you see they have some competitiveness with you? Oh, yeah.
I think the objective, or let's say the application that they are looking is quite different. So actually, we've tried to collaborate in the past, but we never found the actual financial means to do it. So
I see.
From what you're saying, I interpret that you're talking about Aaron Gedanken. So I know him for many years. So I have been in Bar-Ilan and gave some lectures there, because sonochemistry, well, there are not so many people doing sonochemistry actually, and there are even less people trying to bring it to the market. So the group of Professor Gedanken is one of the very few examples.
Yeah.
And so basically what we were trying to do back then, actually he's retired for many years, but he's so active that he's still doing some science, is to actually sandwich the textile between the bags. And then you have better impregnation, because the way they are using it right now, you have to expect some random appearance of bubbles. And then indeed, all these nanoparticles, silver, can provide some properties to the textile to be more bactericide, or you can improve, let's say, for hospital bed sheets and all this stuff. That's a very interesting proposition. But well, sometimes combining two solutions not necessarily give, or you have to test it, and to test this sort of things, you need money and time.
Right. And the second question is about this needleless liquid injection, and it's very close to that one is used in the inkjet printers. So, isn't it?
Yeah, definitely. I mean, I collaborate with scientists that have been looking at the problem, not only from needle-free injections, but also inkjet printing. But the technology they use is relatively different. So first, they typically use a piezo or some sort of oscillating mechanism to eject the little droplets. And typically they are interested in a smaller volume control and less velocities. Because if you start shooting, well, we didn't do the experiments, you don't want to make a hole through the paper, let's say. But of course, I learned a lot from the field. So they've been working for more than 50 years in improving the printing, inkjet printing. So there's a very close relationship, so you're right.
Because this was kind of reminded me when I was in school, we had like those lecture about those cumulative, how to say, the cumulative striking of the, so for example, it can be used in some kind of the rockets or somewhere else. This, so at that high speeds, for example, metals also behaves like liquids. So yeah, so in this case, like your application might be find some better applications.
Can you
like
explain? So you have liquid metal, or you heat a metal with a liquid jet?
No. You have an explosive, right, which is accelerate the metal to such a speed. I mean the hypersonic speed, and at that high speed, the metals also start to behave like liquids. And actually, this is already shown quite a long time ago that actually these metals behave like your liquid. You're doing the injection into the skin, right? I mean that the sprinkle of the liquid. So the metals do the same way, but it could be also impregnated inside another metal.
Okay.
So maybe in such a small volume, you can use it as some not sure, that's the coating applicator, and which I think will be having like a huge demand in aviation, aerospace industry, I believe.
No, definitely. I mean, in some of the proposals, I write that, like, let's say I'm focusing on injecting into skin, but with the same technology, you could how to say, improve coating, or even this new revolution on 3D printed organs. If you have a tiny little cell and you are printing, if you come with a needle, the moment that you retract the needle, then everything changes. So if we could also inject the nutrients or bring some cells in close proximity without having to come with a solid needle, that could be interesting experiment.
Yeah, all right. Thanks. It's just was curious.
No, thanks. Thanks for your question.
Hi, David. Yeah, thanks for the very interesting talk. So I was, I guess, interested in sort of, like what roles do you actually play in the businesses that you've founded? And, obviously, since you're a professor, like, how do you see your role as those companies grow? So do you expect to, become more involved or less involved? Yeah.
Well, thanks for that question. It's one I typically get, definitely when I'm requesting money from the government and things like that, because obviously you don't want to siphon public money to private entities. So I think that the protection shield that I have is that we have very clear agreements with the university. So it's a public institution, or at least non-profit. And I don't have, let's say, I have never been in, let's say, in the payroll of the first company. And when we create the other one, the needle-free injection, one possibility is to reduce my employment at the university, and I go work 2-3 days for the company so that I can accelerate the scientific development. That already tells you that even though 10-15 years ago, I might have been the proper CEO for the company, now that I have built my career and I like so much sitting at this interface between industry and the university world, then I don't see myself abandoning my academic path just to go for one particular invention, because in 5 years I might come up with a new invention. So I see myself as sort of ideas generator and try to push it into society as far as possible. And at some point, it should take off by itself by another team or CEOs or CTOs even. I think I answered both your questions all messed up, or did I?
Yeah, thank you. So I guess, are you currently like a CEO or?
Yeah, for the needle-free injection, I'm more like everybody, a CEO, CTO. I have a bit of support from commercial activities from a colleague, was in one of the pictures you saw there. We are actually actively recruiting for CEOs that could take things in hand, because I'm even running now a feasibility study that I got subsidy from the Dutch government. But obviously your mind gets stretched in different directions, because one thing is the scientific type of curiosity-driven research that I got money to execute, and the other one is the user requirements and legislations and CE marking. Is it a medical device or not? So the jargon and the things you have to dive in are completely different. So I can still handle, but there's a limit. So I know I'm reaching that limit. So if you know of an interesting potential CEO, just let them know. We are recruiting now.
Yeah, thanks for that. Yeah, maybe someone in our audience knows very ambitious CEO type people.
David, thanks again for your talk, because it was really inspiring, and I think it's also you were discussing a lot of choices and dilemmas that I think many people on this call have, and I definitely do have. So I wanted to ask you about your decisions regarding patenting the technology, because you mentioned that you actually feel the patents. Yeah, but I think that especially in your position where you're somehow on the interface between academia and business, that's very often a question, like what to publish, what to patent. We had a separate talk on this just a week ago. So I'm just curious, how do you decide which sort of technology or what actually to disclose, what not to disclose? A bit of guidance in this area would be, I think, helpful to all of us.
Yeah, so that is a very important question. And so my answer is very personal, because I know every country and even each university has specific agreements. So the US, for example, if you have an idea in your free time at home, it's yours, and then the university is lucky if you give them participation. In the Netherlands, even if I'm on a Sunday sitting in the garden, I have an idea, I have to go and negotiate with the university before anything can happen. So there are some things that is worth protecting, and sometimes there are things that you better keep it as know-how. And it's very hard to tell a priori without knowing what is a specific invention or what is a specific application that you're looking at. My advice would be to, first of all, if you are not working alone, discuss with the other co-founders or people around the idea. And typically you might get some good information from your patent office or valorization unit. So every university has some sort of office. I don't know which name you guys have. But just whenever you have something that, hey, this could be interesting, typically they can help you doing some sort of background search or connecting to some lawyers, just to check if the idea kind of makes sense. And sometimes what can happen is that you patent the idea, but you don't need to protect it in the long term. So this is what we did with the first company. We had some papers that actually we tried to delay so that the patent will be first. But then when the patent was published, you already claimed the knowledge. You have two options: to protect it in specific countries or worldwide, but that can be very expensive. Or at some point, just don't protect anymore. And then since you have an advantage over the competitors, you just keep know-how for yourself. So the patent is there. We are not paying anything to protect it. But nobody has tried to copy it because it might be difficult, or, well, there might be many reasons why you abandon a patent. So in our case, the product is being sold. We haven't faced any harsh competitors, and we didn't have that much money to start protecting it. Let's say if I wanted to protect in Europe, but then somebody in China wants to start doing it, they can do it. So that's a fight that we decided not to enter.
Interesting. So basically you play with sort of like with a time advantage that you protect it during the time that you need really to go into the details of the technology. And it's just for your competitors, I think it's just very, very difficult to copy it. It will take lots of time. You have this time advantage, so you can skip the investment into extension of the patent, right?
Yes, and also depending on the invention, there are investors that would only put money in your idea if you have a patent. So sometimes if you're confident that you don't need external investors, you don't need to patent, you go on your own, you fly on the radar, then you can create the product. And if you can protect somehow your invention, maybe you don't need to patent. So it's not really mandatory. But sometimes it's like a strategic move. And it's also a backup plan, because having a patent also counts for your academic career. Or imagine everything goes to the docs and the product never really makes it to the market or becomes a flop. At least you have the patent there, so it's seen as a publication. So there was knowledge, there was time invested in it, and it's an interesting exercise. But not everybody needs to patent, and sometimes you can also just leave it, like we did with the first patent. The second one just got published last year, and we're actually planning to build more knowledge on top of it and have some sort of spin-off patents from it. It's complete different strategy on each application.
Okay, I see. Thanks.
Okay, so we've just hit 5 p.m. well, in Singapore anyway. So does anyone have a final question for David, or are we all okay?
I have a final question.
Okay.
Hopefully you could perhaps point me in a certain direction of what you're currently doing with hydrogen.
So basically what we are designing is novel types of electrodes where, again, using the same trick of defects, we can control where the bubbles are being created. And then we are looking at what type of electrode dimensions or configurations are needed to have better control on the appearance, growth, and detachment of bubbles. And we have, I think, like 4 papers on this topic and 1 or 2 more in the making right now. But yeah, basically it's more from a fundamental point of view. So we are following a bit of a physics approach. We control one thing, then you change a few parameters. But the PhD student working in this project has the ambition, maybe in a couple of years, to explore. Maybe there's a possibility also to start up a company, which I'm more than happy to help with that. But I don't know if that is already interesting for you. Of course, we have a couple of other big review papers on solar hydrogen. So if you cannot find it, drop me an email. But it's a big paper with like 50 co-authors, and a review from last year on how bubbles influence the energy efficiency of electrochemical reactions.
Oh, very interesting. I'll have a look at that. And perhaps there may be some applications with some of the work that CARES is doing with CO2 electro reduction.
Yeah, there's a lot of relationship because, well, you change the liquid or the potential value or sign, and then you can do different chemistry. But we are looking at the geometry itself, which teaches you a lot.
Oh, thank you.
Yeah, I have to check this paper definitely.
Yeah,
so the last one is in Joule, and the other ones are in energy and environmental science, Langmuir, I think. Oh, well, if it's not, just drop me an email. I can send you the whole collection.
Yeah, I definitely will, because I think it's going to be a very, very strong link between what you're doing in the field in CO2 electro reduction, because yeah, actually bubbles matter really a lot there.
Yeah.
Thanks.
All right.
Yeah, anyone...
Well, thanks for the opportunity. I thought you were about to wrap it up.
Oh, no, I'm just saying to everyone that the link for your website, David, I put it in your biography when I circulated the email. So if anyone's looking for David's website, it's in the email I sent. So yeah, just so they know where to find you and your contact details. Yeah.
Excellent. All right. Well,
great.
Have a nice day.
Yeah, thank you so much for joining us today. We really appreciate your time and your expertise.
My pleasure. Bye-bye.
Yeah, thanks again. It was really great.
Thank you.